Okay, so this video is going to cover section 11.5, which is density and displacement. So we're going to be talking about kind of, first of all, how we use water displacement to measure the volume of an irregular shaped object that we can't just calculate the volume for. And then we'll talk about what density is and how we can use that with our volume calculations. Before we do that, just a quick note, I will make sure that the answers to Friday's homework are posted on the Canvas page for Friday. So make sure you go back and look at those. We won't have time. We're not going to obviously be able to go over them today, but make sure you look at those answers and you have at least a chance to kind of see which ones you're getting right or wrong, or what ones you might have questions of. Remember, a lot of those are challenges, so don't be too concerned if you're not 100% sure how to do them all. We're really looking for the thought process, and then knowing that on the test we're going to have a simpler application of volume on there. So here we go. The first thing I'm going to want you to do here is pause the video when you're answering this question, or think about this question for just about 30 seconds before you actually move on. But we've got a glass here full to the brim with, root beer. We're going to take a scoop of ice cream and put it in that glass and think about what is going to happen when you do that. And so hopefully you probably even saw the picture there. When you put that scoop of ice cream in, it is going to displace some of that root beer, and it is going to end up all over the counter. So when you place an object in water, the big idea here is that it's going to displace a volume of water that is equal to its own volume. It takes up just as much space as that water would have. And so if you put something in the water, it is going to raise the water level by some amount. And that amount that the water level has raised, that volume of new water there, not new water, but what looks like new water, is going to equal the volume of that object. And we can use that to measure the volume of oddly shaped items. And so here we've got a picture of Archimedes here in his bathtub. If you've ever heard the phrase Eureka, that actually, the legend goes that Archimedes was supposed to help the king figure out if the crown that he had gotten was actually made out of pure gold or if it had been made of some cheaper metal. And he obviously didn't want to take the thing apart or break it and find out, or melt it back down and see its density by putting it into a nice shape. And so what he did was he actually submerged it in the bath when he was supposedly taking a bath, saw how much the water level rose, and was able to calculate the volume of the crown, weigh it, calculate its density, and determine whether or not it was pure gold. And when he had that eureka moment, he got out of the bathtub and ran down the street naked, which is great, I guess. So let's take a look at this one. Mary Jo wants to find the volume of an irregularly shaped rock. She puts some water in a rectangular prism with a base that is 10 by 15 centimeters. And then she places the rock into the container, and the water level raises by 2 centimeters because that rock took up space in the water. Now, here's the big key, and the part that people always have a little bit of trouble with here. And this is the idea that it's this new slice of water that we actually care about. It's not really new water. It's just water that's been pushed up higher. But we want to find the volume of just this little tiny slice here. That new slice, not really new, but whatever, that slice of water is the part that has been displaced by the rock. And so here we've got basically what is a 10 by 15 by 2 inch rectangular prism. And so that's why you can see they've taken 2 times 10 times 15 and gotten 300 cubic centimeters. And so that is the volume of the rock. Now, a lot of you, I believe you might even do this in like earth space science or something. If you do this in a science class, you're not going to use a 10 by 15 rectangular prism. You'd actually use a graduated cylinder that would have markings along the side in volume. Usually graduated cylinders in a science class are going to be marked in milliliters. And so you'd actually be able to measure how many milliliters of water it changed directly. You wouldn't have to calculate the volume like this. And so, you'd be able to see, okay, the volume of water went from 700 milliliters up to 1,000 milliliters. And so it increased by 300 milliliters. And you'd know, well, water, 300 milliliters is the same as 300 cubic centimeters. And so that's the volume of the rock. So in a science class, obviously we don't do those volume calculations. This is a math class and we're learning about volume. So we're doing the volume calculations. Sorry. They'll be simple. They'll either be rectangular prisms or cylinders. Okay. Next question here is, what would you rather be hit with? Imagine it's going to drop on your head, 50 pounds of bricks or 50 pounds of feathers. Go ahead and pause the video. Think about that. And don't hit anybody with bricks. Okay, so no matter what you said here, one of the things we've got to start to realize is 50 pounds of bricks and 50 pounds of feathers weigh exactly the same. What the thing is in your head that wants you to say feathers is that feathers are a lot less dense than bricks. 50 pounds of feathers would take up a lot of space, even though they'd still actually weigh the same amount. And so this idea of density is how much mass or matter is present in a given volume. And so denser things are heavier for their size, like bricks, and then less dense things are lighter for their size, like feathers. They might have the same weight, but the feathers are going to have to take up more space than the bricks in order to have that weight. And I'm using weight and mass interchangeably. I get it. They're not the same. Math class, we're not in science class. Sorry, science teachers. Okay, so our formula for density here, density is just going to be the mass of the object divided by the volume. So you're going to see things like grams per cubic centimeter is a common one in the metric system. You'll in the U.S. system, you might see something like cubic centimeter, ounces per cubic inch, or pounds per cubic foot. Things like that. Those are all going to be volume or measures of density, right? Some of these are actually mass, and some of these are actually weight. But again, we're going to live with that for now. Okay, so something like this might be a good place to start. Calculate the density of a cylinder of trapezoidal prism of gold. Of a trapezoidal prism of gold that weighs 1,350 grams. It says all the measurements are in centimeters. So since our density relies on us knowing the mass and the volume, the first thing we've got to do is, we know the mass, we're going to calculate the volume. And so this is a prism. The volume is going to equal the area of the base times the height. It is a trapezoidal prism, so we've got the area formula for a trapezoid, 1/2 times B1 plus B2 times H. And then the height of the prism is 10. And so we'll go ahead and do that. I'm just going to go ahead and simplify it as I go since I don't have a calculator right with me. So 1/2 times 7 times 2 times 10. Well, that would be 7 times 2 is 14. 1/2 of that is 7. So 7 times 10 is 70 cubic centimeters. Then I can go back up and say, now once I know my volume and I already know my mass, density is the mass, 1,350 grams divided by 70 cubic centimeters. And I guess I should probably pull out a calculator. And so I'd want to take 1,350 divided by 70, and I get what would essentially round to 19.3. So my density is 19.3, and since this was grams and this was centimeters cubed, my units would be grams per cubic centimeter, which is a really common density unit in, as long as you're in the metric system. Okay, so that's just a straight calculation of density. You can kind of see these are basically just applications of volume like we were doing Friday. You're going to find the volume, you're going to do something with it. Same thing here. You found the volume to do something with it. Okay, last example we're going to do is just a little bit more involved because we've got kind of an extra step of kind of putting the things together. We're going to do a displacement problem, then we're going to throw it into a density problem, and we're going to have lots of fun. So a clump of metal with a mass of 351.4 grams. So I'm going to say mass 351.4 grams is dropped into a cylindrical container, causing the water level to rise 1.1 centimeters. The radius of the base of the container is 3 centimeters. And we want to find the density of the metal. And then use this table to figure out what it is. So eventually, we're going to want to find the density here. And since density is mass divided by volume, we need to figure out what the mass is and what the volume is. Well, they tell us the mass. And we've got to find the volume. The deal here is instead of being able to calculate the volume because it's a shape we know that we dropped it into this water and the water level rose 1.1 centimeters and it was a cylindrical base of 3 for the radius. And so we can think, here I can draw a picture of that. You've got this cylindrical container. There was the water level there. And when I drop this clump of metal in, the water level rises by, there was the old level. There's our new level. It rose by 1.1 centimeters. And the radius of this is 3. And so what I'm trying to do is basically to calculate the volume of this little mini cylinder right here. Right? That's a little mini cylinder of new slice of water. So just like any other cylinder, I'm going to calculate the area of the base, which I know since it has a radius of 3, I can go pi times 3 squared or get 9 pi. Then to calculate the volume of that water that was displaced, I'm going to take 9 pi times 1.1. This is not the time to leave things in exact form, so I'm going to go straight to Desmos. 9 pi times 1.1, and it says 31.3, and that was all in centimeters, so cubic centimeters. Now I can go back to my density equation. Since I know the mass was 351.4, and I know my volume is 31.3, I can calculate my density by just dividing 351.4. So 351.4 divided by the previous answer gives me 11.298, so essentially 11.3. My density is, my density is 11.3. I'm just going to we'll do this. From there, I'm going to go way down here. Density is, I forgot what the number was already, 11.3. Again, since my mass was in grams and my volume was in cubic centimeters, grams per cubic centimeter. So now this gives us an option to say, okay, well, if that's the density, let's go ahead and look through our list and find one that is the same. Well, hey, there's one that's pretty close. 11.3 grams per cubic centimeter gives me lead. So whatever this metal was, it was lead. It's the only one that's even close on our list. Okay, so that's kind of the idea here. Again, it's very, very similar to what we did on the last one, just this idea of, okay, now I'm going to use displacement to calculate the volume, then find the density that way. So biggest thing I can always say here, biggest thing, when you're doing these displacement problems, find the volume of the new slice. Right? Whatever they dropped in there, look at that new slice. Here, when they dropped it in, the water level rose by 1.1. That's the height of the cylinder that you are finding the volume of. There's a reason they don't tell you the height of the container. That doesn't matter at all. So base, the height is the amount the water rose. You're good to go. With density questions, density equals mass divided by volume. Most of them, they're going to give you the mass or the volume and ask you to calculate the density, or you might have to find the volume and then calculate the density. But they could ask you to go backwards, right? If they gave you the density and the volume and asked you to calculate the mass, you could do that. Might not be a bad idea just to kind of show you what that would look like. If I had a problem where I said the density of this thing was, let's just look at the list. Give me one that actually makes sense here. Let's just say the density of something was 2.8 grams per cubic centimeter. And I happen to say that the volume was, 73 cubic centimeters. If I wanted to find the mass, I'm still using the exact same equation. Density equals mass divided by volume. I'm just plugging into the things I know. So density is 2.8. Mass I don't know. Volume I do know. And to solve that equation, I can multiply by 73 on both sides. And then I could just punch that in my calculator. 73 times 2.8 is 204.4. So my mass would be 204.4 grams. Again, grams per cubic centimeters gives us grams for our mass. We're talking about grams. Okay, so for the homework, keep it a little shorter because yesterday's or Friday's was really long. I'm sorry about that. Page 559, we're just doing questions 1 through 7. I'm going to leave these up in the video just for a second so that you give a chance. You could pause the video here, do these questions, go forward 3 seconds, pause the video, do those questions. So on these, it's all just displacement problems. On these ones, you need this table. So they're asking you for the mass of a solid block of aluminum. If those are the dimensions, that's very similar to what I just did. You're going to find the volume and then use that density. On this one, which has more mass, that thing or that thing. So find the volume, multiply by the density, find the volume, multiply by the density, see which one weighs more. This one is very, very similar to the example we did with the cylinder. You're going to find the volume with displacement, and then you're going to do mass divided by volume and see what it is. And then you're going to do number 7. This one's kind of you get the mass, you find the volume with displacement, you calculate the density, and you look up what the thing is. So very, very similar there. You're doing 1 through 7. So here's 7. There's 4, 5, 6. And there's 1, 2, 3. They're all right there for you. And there's an answer sheet on the Canvas page, either right below this video if you're watching it yourself, or you'll have to go to the Canvas page yourself if you're not watching it yourself. See you Tuesday.